We have been told, for most of our lives, that Jupiter is the good guy, the gentle giant, the silent guardian standing watch at the edge of the inner solar system, pulling comets and asteroids into its gravity before they can reach us. We have been told it is peaceful, a swirling painting of soft orange and cream and rust, so beautiful it almost does not seem real. A planet that minds its own business, drifting quietly through the dark, keeping the rest of us safe. But that is not Jupiter. That has never been Jupiter. The truth is something else entirely. The truth is that Jupiter is one of the most violent, catastrophic, and terrifying objects in the entire solar system. It is a world where storms have raged for longer than human civilization has existed, where radiation could kill you before you even got close, where the pressure builds so intensely as you descend that even the toughest materials ever engineered by human hands would be crushed and dissolved in seconds, where winds move so fast they do not just push things around, they tear them apart at the molecular level. And here is the part that makes it all stranger and more unsettling than it might first appear. Jupiter does not look dangerous. From a distance, it looks like a work of art. It looks calm. It looks almost inviting. And that gap, the space between what it appears to be and what it actually is, that is what makes Jupiter so deeply, fundamentally frightening. This is not a story about a protector. This is a story about a monster. And like the best monsters, it has been hiding in plain sight the whole time. Let us start with what we think we know, because it is important to understand the version of Jupiter that lives in our heads before we take it apart completely. For generations, scientists and science communicators have described Jupiter as Earth's bodyguard. The idea is straightforward enough. Jupiter is enormous. More than 1,300 Earths could fit inside it, and its gravitational pull is so immense that it acts like a kind of cosmic vacuum cleaner. Asteroids and comets that wander into the inner solar system often get swept up by Jupiter's gravity. They fall into the giant planet instead of continuing their journey toward Earth. Without Jupiter, the thinking goes, our planet would have been bombarded far more frequently. Life might never have taken hold. We might not be here at all. It is a compelling story. It is the kind of story that makes the universe feel almost friendly, as if the cosmos arranged itself with us in mind, placing this enormous guardian right where we needed it. School children learn it. Documentaries repeat it. It has become one of those comfortable facts that people carry around without questioning. But the comfortable version is not the complete version. The reality is that Jupiter's relationship with the inner solar system is complicated in ways that make the simple bodyguard story feel almost embarrassingly incomplete. Yes, Jupiter does sometimes catch objects that might otherwise reach us. That part is true. But Jupiter also destabilizes things. Cosmic drifts beyond the stars plays for hours. No ads, no interruptions, no reaching for your phone. 5 full night sleep experiences, one-time purchase. Begin now at mycosmicdrift.com. It throws objects around. It has, over the long history of our solar system, flung asteroids out of stable orbits and sent them hurtling inward toward the rocky planets. Some of the impacts that shaped early Earth, the ones that may have delivered water and organic molecules to our planet's surface, were likely the result of Jupiter stirring the cosmic pot. The same gravity that sometimes shields us has also, at other times, served as a kind of cosmic slingshot, sending danger directly our way. Jupiter is not our protector. Jupiter is a force of nature so massive and so powerful that its influence is everywhere, and like most forces of nature at that scale, it does not discriminate. It does not protect. It simply does what physics demands it do. And sometimes that means flinging a mountain-sized rock toward the inner planets with no more consideration than a child flicking a marble across a table. This is the first lesson Jupiter teaches. Gravity at this scale is not gentle. It is not safe. It is one of the most powerful and impersonal forces in existence, and Jupiter has more of it than any other planet in our solar system. To begin to understand the scale of Jupiter's gravity, you have to first understand the scale of Jupiter itself. And this is where numbers start to feel surreal. Jupiter's diameter is about 11 times the diameter of Earth. Its mass is more than twice the combined mass of every other planet in the solar system put together. Saturn, Uranus, Neptune, Mars, Venus, Mercury, and Earth, all of them combined. And Jupiter still outweighs the whole group by more than 2 to 1. It contains roughly 70% of all planetary matter in the solar system. Everything else is almost a rounding error. When you stand on Earth and look up at the night sky, Jupiter is one of the brightest objects you can see with the naked eye. It looks like a bright, steady star, outshining almost everything else. That brightness comes not from any light of its own, but from reflected sunlight, and the fact that it appears so bright despite being hundreds of millions of miles away tells you something important about just how large a surface it presents to the sky. But brightness and size, as extraordinary as they are, do not quite capture what Jupiter actually is. To do that, you have to go closer. You have to think about what it would mean to approach it. Imagine you are on a spacecraft. Not a real spacecraft, because no real spacecraft could survive what I am about to describe. But imagine one anyway. You are approaching Jupiter from a safe distance, and you can see it ahead of you, growing larger in your window with every passing hour. At first, it is just a bright disk, the familiar banded face that we see in photographs. The bands are cloud systems, vast streams of gas moving in opposite directions at different latitudes, and even from a distance you can see that they are not still. They are churning. They are active. They look like something alive. As you get closer, you begin to notice something else. The colors are not soft. In photographs, Jupiter often looks gentle, the oranges and creams muted and warm. But up close, those colors are the surface expression of violent chemistry. The bands are made of ammonia ice, ammonium hydrosulfide, and water ice, and the different colors reflect different chemical compositions and different altitudes within the cloud layers. The pale zones are areas where gas is rising. The dark belts are areas where gas is sinking. The whole planet is one enormous convection system, constantly cycling material up from below and pushing it back down again. The winds in those bands move at speeds that would make a Category 5 hurricane on Earth feel like a gentle afternoon breeze. In Jupiter's atmosphere, wind speeds regularly exceed 500 kilometers per hour. In some regions, they reach 600. In some localized features, they go higher still. These are not gusts. These are sustained, persistent winds that have been blowing at those speeds for longer than any human civilization has existed. They do not stop. They do not calm down. They are a permanent feature of a world that has never known stillness. And then there is the storm. You have probably seen it in images. The Great Red Spot. It sits in Jupiter's southern hemisphere, a vast oval of swirling cloud that is impossible to miss because it is, even by Jupiter's standards, enormous. At its largest historical measurements, the Great Red Spot was wide enough that 3 Earths could have fit inside it side by side. Today, it has shrunk somewhat. It appears to be contracting over time, but it is still larger than our entire planet. It is still by any reasonable measure, the biggest storm in the solar system. But the word storm undersells it. On Earth, storms are temporary. They form, they rage, they exhaust themselves, they dissipate. The Great Red Spot has been continuously observed for at least 350 years. Some researchers think it has been there for much longer than that, possibly for centuries before the first telescopes were pointed at Jupiter. It has been raging without pause for longer than the United States has existed, longer than the Industrial Revolution, longer than the printing press. It was already old when Isaac Newton was formulating the laws of motion. Think about what that means for a moment. A single storm, one continuous hurricane-like vortex that has been spinning without interruption for at least 3.5 centuries, and possibly much longer. Why does it persist? The answer lies in the dynamics of Jupiter's atmosphere, and it tells you something important about why Jupiter is so different from anything we experience on Earth. On our planet, storms are powered by heat from the surface below and cooled by interaction with the upper atmosphere. They pull energy from temperature differences, and when those differences equalize, the storm loses its driving force and dies. But Jupiter has no solid surface. There is no ground to interact with. The atmosphere extends downward for tens of thousands of kilometers, and it never hits a boundary. It just keeps going, transitioning from gas to liquid to something more exotic as the pressure builds. A storm on Jupiter does not lose energy by interacting with the surface, because there is no surface to interact with. It simply keeps cycling, kept alive by the enormous internal heat that Jupiter radiates from its own gravitational compression. Jupiter actually radiates more energy than it receives from the Sun. The planet is still slowly contracting under its own gravity, and that contraction generates heat, and that heat drives the atmosphere from below. Jupiter is, in a very real sense, still cooling down from its own formation billions of years ago. The energy released by that slow contraction is part of what keeps the Great Red Spot alive. Now, you might be wondering what it would actually feel like to enter that storm. The honest answer is that no spacecraft has survived the attempt, and the reason is instructive. The winds at the outer edge of the Great Red Spot can reach speeds of around 600 kilometers per hour. But that is almost the least of your problems. The real issue is the structure of the storm itself. The Great Red Spot is not just a horizontal swirl of wind. It is a complex three-dimensional structure with vertical components. Gas is being drawn upward in some regions and pulled downward in others. The pressure gradients within the storm are intense. The temperature variations are extreme. And the turbulence, the chaotic, unpredictable movement of gas at the boundaries between different regions of the storm is violent enough to tear apart anything we could currently build. In 1995, NASA sent the Galileo probe into Jupiter's atmosphere, not into the Great Red Spot specifically, but into the atmosphere of the planet in general. The probe was designed to measure wind speeds, temperature, pressure, and chemical composition as it descended. It was a remarkable piece of engineering, built to withstand conditions far beyond anything encountered on Earth. It lasted 58 minutes before the pressure and heat destroyed it completely. In those 58 minutes, it descended about 160 kilometers into the atmosphere, which sounds like a lot until you realize that Jupiter's atmosphere is tens of thousands of kilometers deep. The probe got through barely more than a fraction of the outer layers before it was obliterated. And here is the part that the Galileo probe's data revealed that genuinely surprised scientists. The winds were not weaker as the probe descended. They were stronger. On Earth, Wind speeds decrease as you go below the upper atmosphere. You expect things to calm down as you go deeper. Jupiter works the opposite way. The deeper you go, the faster the winds blow, because the deeper layers are driven by the planet's internal heat, rather than by solar energy at the surface. The storm does not thin out and dissipate as you go down. It intensifies. This is a planet where going deeper does not mean finding safety. It means finding something worse. But even the winds, as extraordinary as they are not the most immediately lethal thing about Jupiter. For that, we need to talk about radiation. Jupiter is surrounded by the most intense radiation belts in the solar system. Earth has radiation belts too. Bands of charged particles trapped by our planet's magnetic field. They are called the Van Allen belts, and they are genuinely dangerous. Astronauts passing through them accumulate radiation exposure. Satellites have their electronics affected. The Van Allen belts are a real hazard that space mission planners have to account for carefully. Jupiter's radiation belts make Earth's look like a mild inconvenience. Jupiter has a magnetic field that is roughly 20,000 times stronger than Earth's. This enormous magnetic field traps charged particles, electrons and protons and ions, and accelerates them to enormous speeds. The result is a radiation environment. Around Jupiter, that is, in some regions, the most hostile place in the solar system outside of the Sun itself. To put this in concrete terms, the region around Jupiter's moon Io, which orbits relatively close to the planet, receives a radiation dose of about 3,600 rems per day. A dose of 500 rems over a short period is lethal to a human being. The area around Io would kill an unprotected human being in less than 10 minutes, before you even got close enough to feel Jupiter's gravity pulling at you significantly. The radiation would have already done irreversible damage to your body. And this is not just a human problem. Electronics are vulnerable too. The charged particles that make up Jupiter's radiation belts can penetrate metal shielding, flip bits in computer memory, damage sensors, and eventually destroy circuitry. Every spacecraft sent to the Jupiter system has to be carefully shielded and hardened against radiation effects. Despite those precautions, the Galileo spacecraft that orbited Jupiter from 1995 to 2003 accumulated significant radiation damage over the course of its mission. When it was finally deliberately crashed into Jupiter's atmosphere at the end of its operational life, it had sustained enough radiation damage to affect some of its systems. The Juno spacecraft, which has been orbiting Jupiter since 2016, was designed specifically to minimize radiation exposure by using a polar orbit that keeps it away from the most intense parts of the radiation belts for most of its orbital period. It still receives significant radiation doses during each close pass. Mission planners track the accumulated damage carefully because there is a hard limit to how much radiation the spacecraft can absorb before it stops functioning reliably. Think about what that means for the prospect of human exploration. To send human beings to Jupiter's vicinity, not to land on Jupiter, just to orbit or pass nearby, would require radiation shielding so massive and so comprehensive that it would represent one of the greatest engineering challenges in human history. The radiation environment is not a minor obstacle to be engineered around. It is a fundamental characteristic of the space around Jupiter, a direct consequence of the planet's enormous magnetic field, and it makes the entire Jupiter system deeply hostile to any form of life or technology that we currently understand. The source of Jupiter's magnetic field is itself a remarkable and somewhat terrifying thing. Deep inside Jupiter, far below the cloud layers, far below where the Galileo probe was, destroyed, the pressure becomes so extreme that hydrogen undergoes a transformation that does not happen anywhere in our everyday experience of matter. Hydrogen, normally a gas, becomes compressed so tightly that its electrons are stripped loose from their atoms. The electrons become free to move, not bound to any particular hydrogen nucleus, free to flow through the material like electrons flow through a metal conductor. The result is a substance called liquid metallic hydrogen. Liquid metallic hydrogen conducts electricity, and when you have an enormous volume of electrically conducting fluid deep inside a rapidly rotating planet, you get a dynamo effect. You get an extraordinarily powerful magnetic field. Jupiter rotates on its axis once every 10 hours, which is extremely fast for an object of its size, and that rapid rotation drives the liquid metallic hydrogen dynamo deep in its interior, generating a magnetic field that extends millions of kilometers into space in every direction. The magnetosphere of Jupiter, the region of space dominated by its magnetic field, is so large that if you could see it from Earth, it would appear in our sky larger than the full moon. Despite Jupiter being hundreds of millions of kilometers away, it is the largest structure in the solar system, other than the Sun itself. It envelops all of Jupiter's moons. It extends past the orbit of Saturn in one direction. It is vast on a scale that is genuinely difficult to hold in your mind. And all of that comes from what is happening in the deep interior of Jupiter. Which brings us to the most disorienting aspect of this planet. The question of what Jupiter actually is on the inside, and why the idea of descending into it is not just physically impossible, but conceptually strange in a way that is hard to fully articulate. Jupiter does not have a surface. This statement sounds simple, but what it means is genuinely bizarre. On Earth, you know where the planet is. You are standing on it. There is a clear boundary between solid ground and atmosphere. You could, in principle, dig through the ground and eventually reach the other side. On Mars, same story. On the Moon, even on Venus, beneath its crushing atmosphere, there is a solid, rocky surface you could theoretically stand on. Jupiter has no such boundary. There is no ground. There is no surface to stand on, land on, or crash into. There is only the atmosphere, growing denser and hotter and more pressurized as you descend, transitioning gradually from gas to liquid to something stranger, with no clear line marking the transition from one to the next. If you were falling into Jupiter, you would not experience a distinct moment where you hit the ground. You would simply experience the environment getting worse, the temperature climbing, the pressure building, the gas around you becoming thicker, denser, more like a liquid. And then you would reach a depth where the distinction between gas and liquid ceases to have any real meaning, where the material around you is so compressed and so hot that it behaves unlike either. And then deeper still, you reach the region of liquid metallic hydrogen, and by that point, you have long since ceased to exist in any recognizable form. This gradual dissolution is, in its own way, more unsettling than hitting a solid surface. There is no impact, no sudden stop, just a slow, relentless increase in the forces acting on you until there is nothing left to act on. The pressure at the top of Jupiter's visible cloud layer is already comparable to the pressure several kilometers below the surface of Earth's oceans. As you descend, it increases rapidly. By the time you have gone a few hundred kilometers below the cloud tops, you are at pressures that would instantly and completely destroy any current spacecraft. By the time you reach the transition zone where gas becomes liquid metallic hydrogen, the pressure is roughly 3 million times the atmospheric pressure at Earth's surface. At these pressures, diamond, the hardest natural substance on Earth, would not just be crushed, it would dissolve. This is not metaphor. Diamonds under sufficient pressure actually do dissolve into liquid carbon in certain models of Jupiter's deep interior. Some researchers have proposed that deep inside Jupiter and Saturn, it might actually rain diamonds. Carbon from the atmosphere gets compressed, forms solid structures, and then at even greater depths, those structures dissolve back into liquid as the pressure becomes too extreme even for solid diamond to maintain its structure. The diamond rain hypothesis has not been directly confirmed because we have no way to observe Jupiter's deep interior directly, but the physics supports it, and it is a useful illustration of what extreme pressure does to our intuitions about solid and stable things. Nothing is solid under those conditions. Nothing is stable. The rules that govern the materials we interact with every day cease to apply, and what replaces them is something stranger and more extreme. The temperature inside Jupiter also climbs to levels that are difficult to contextualize. At the cloud tops, the temperature is roughly minus 145 degrees Celsius, intensely cold. But as you descend, it rises. Somewhere in the liquid metallic hydrogen layer, the temperature reaches approximately 17,000 degrees Celsius. That is 3 times hotter than the surface of the Sun. Deep in the interior, near the core, it may reach around 36,000 degrees Celsius. At those temperatures and pressures, the concept of distinct chemical elements starts to break down. Atoms are stripped of their electrons. Matter exists in a plasma-like state that is more like the interior of a star than anything we encounter on Earth. Jupiter's core is not a rocky ball in the way Earth's iron core is a metallic ball. It is a region of extraordinarily dense, hot material, possibly a mixture of rock and metal and ice that has been compressed and heated beyond recognition, surrounded by the vast envelope of liquid metallic hydrogen, and then the outer layers of liquid and gaseous hydrogen and helium that make up most of the planet's volume. Jupiter is in every meaningful sense a world that is fundamentally alien to our experience of matter and physics. The rules work the same physics governs every layer, but the conditions are so extreme that the outcomes of those rules look nothing like anything we can touch or see or measure in our everyday lives. And this brings us to what may be the most thought-provoking aspect of Jupiter's nature, a question that sits at the intersection of planetary science and existential unease, the question of what Jupiter almost was. Jupiter is not a star, but it very nearly could have been something more like one. Stars form when a cloud of gas collapses under its own gravity and the center becomes dense and hot enough to ignite nuclear fusion. The process of fusing hydrogen atoms into helium and releasing enormous amounts of energy in the process. The Sun is powered by nuclear fusion. It has been for about 4.5 billion years, and it will continue to be for another 5 billion or so. The minimum mass needed to ignite hydrogen fusion is roughly 80 times the mass of Jupiter. Jupiter's mass is, as we have established, already enormous by the standards of planets, but it is still only about 1,000th the mass of the Sun. It would need to be 80 times more, massive to ignite nuclear fusion and become a true star. That sounds like a comfortable margin. But there is a category of objects between planets and stars, objects called brown dwarfs, and the lower mass limit for a brown dwarf is about 13 times Jupiter's mass. Brown dwarfs do not sustain hydrogen fusion, but they do briefly fuse a heavier form of hydrogen called deuterium, and they produce heat and faint light as they slowly cool. They are, in a sense, failed stars. Stars that almost made it but stopped short. Jupiter, at one mass, is safely below the brown dwarf threshold. But in the early solar system, when gas and dust were still being swept up by forming planets, there was a period during which Jupiter was actively growing. Material was accreting onto it. Its mass was increasing. We know it did not grow large enough to become a brown dwarf, clearly, because it exists in its current form. But the universe is full of systems where one or more of the forming gas giants did grow large enough. Systems where what might have been a planet became something much more energetic. If Jupiter had been born in a different region of the protoplanetary disk, with more material available to accrete, it might have grown to 13 times its current mass and ignited deuterium fusion. Our solar system would have had 2 suns, and the consequences for Earth would have been profound. A second sun in our solar system would have fundamentally altered the energy budget of every planet. The orbital dynamics would be chaotic. The habitable zone, the region where liquid water can exist on a planetary surface, would shift and change depending on the positions of both stars. Earth might still exist, but it would be a very different place, if it existed at all in a stable orbit. Life as we know it might never have had the chance to develop. We exist, in part, because Jupiter did not accumulate quite enough mass, because it fell short of the threshold for brown dwarf status by a factor of 13. That margin is the reason we are here. And when you think about it that way, Jupiter starts to seem less like a benign giant and more like a cosmic near miss, a world that came close enough to stellar ignition to matter, but stopped just short of the threshold that would have made our existence impossible. The distinction between Jupiter and a failed star is not some vast, comfortable gulf. It is a factor of 13. And the universe is full of examples where the outcome was different. This near-miss quality, the sense of Jupiter as something that came very close to being something else entirely, runs through the history of its formation and its influence on the solar system. Jupiter did not simply appear in its current orbit and stay there. The history of the solar system's formation involves Jupiter moving dramatically in ways that reshaped everything else. Current models of solar system formation, particularly a model called the Grand Tack hypothesis, suggest that Jupiter formed farther out in the solar system and then migrated inward. Drawn by gravitational interactions with the disk of gas and dust that surrounded the young sun, it migrated all the way to roughly the current position of Mars before reversing course and moving back outward, pulled by the forming Saturn. This inward and then outward migration had enormous consequences for the inner solar system. As Jupiter moved inward, it swept through the region that might otherwise have become the asteroid belt and the inner rocky planets. It stirred up material, scattered objects, destroyed some of the protoplanetary material that might have accreted into larger planets in the inner solar system. Mars, which should theoretically be much larger based on the amount of material available when it formed, is stunted, only about 1/10 the mass of Earth, almost certainly because Jupiter's migration scattered so much of the material that Mars would have needed to grow. And the asteroid belt itself, rather than being the remains of a planet that was somehow destroyed, is more likely the remains of a planet that never formed in the first place. Jupiter's gravity stirred the material in that region so thoroughly that the objects there could never come together into a larger body. Every time pieces started to aggregate, Jupiter's gravitational influence would disrupt the process. The asteroid belt is a monument to Jupiter's violence, a region of the solar system where a planet tried to form and could not, because Jupiter would not allow it. So Jupiter's influence during the early solar system was not protective. It was disruptive. It was a force that scattered material, prevented planet formation in some regions, sent debris raining down on the inner planets, and reshaped the architecture of the entire solar system. The fact that Earth survived this period of chaos and eventually became habitable is itself somewhat remarkable. The violence of the early solar system, the period called the Late Heavy Bombardment, when the inner rocky planets were subjected to an intense period of impacts from asteroids and comets, was almost certainly connected to the gravitational dynamics of Jupiter and the other gas giants. Jupiter did not cause all of this harm by itself, but its gravity was a central driver of the complex dance of objects that led to billions of years of intense bombardment. This is the context in which Jupiter exists, not as a protector, but as the single most dominant gravitational influence in the solar system after the Sun itself, a force that has shaped everything, that continues to shape everything, and that does so without any regard for the consequences. Let us come back to the present and think about what it would actually be like to approach Jupiter today. Not to descend into it. We have already established that this ends in dissolution and death, but simply to get close, to orbit it, as the Galileo spacecraft did for 8 years, or as Juno has been doing since 2016. As your spacecraft approaches Jupiter from the outer solar system, the first thing you notice, before any of the visual changes, before the disk grows large enough to show its bands clearly, is the radiation. The instruments aboard your spacecraft begin to register increasing levels of energetic particle bombardment. The radiation environment of the Jupiter system begins well before you can see the planet clearly with your naked eye. The magnetosphere extends millions of kilometers into space, and you are already inside it long before the planet appears large in your window. The Juno spacecraft, on each of its close passes, near Jupiter's cloud tops, travels at speeds of roughly 210,000 kilometers per hour relative to the planet. At that speed, it passes through the most intense part of Jupiter's radiation belts quickly, which is part of the design. It is meant to minimize the total radiation dose absorbed by passing through the worst regions fast. Even so, the accumulated radiation over the course of Juno's mission has been significant. The spacecraft carries a radiation-hardened vault for its most sensitive electronics, a titanium box designed specifically to shield the spacecraft's brain from the most damaging particles. The Galileo spacecraft, which spent years in Jupiter orbit rather than making quick passes, accumulated far more radiation damage. Scientists tracked the degradation of its instruments over time, watching systems that were designed to last begin to fail earlier than planned, because the radiation environment was simply that hostile. No human-crewed spacecraft currently designed or even seriously proposed could survive anywhere near Jupiter for any extended period. The radiation alone would be lethal. But there is something even more viscerally strange about what you would experience approaching Jupiter that goes beyond the physics of radiation and gravity. It is the sound. Space is a vacuum, and sound cannot travel through a vacuum. But radio waves can, and Jupiter generates an extraordinary cacophony of radio emissions. Its powerful magnetic field, interacting with the streams of charged particles, the volcanic activity of its moon Io, injecting material directly into the magnetosphere, the complex plasma dynamics of the entire Jupiter system, all of this generates radio wave emissions that were first detected on Earth in the 1950s. When those radio emissions are converted into audio frequencies so human ears can hear them, what you get is something genuinely eerie. There are bursts and crackles, long, deep rumbles, high-pitched screams, rhythmic pulsing, chaotic noise. It is not like static. It is not like any familiar sound. It is something that feels alive and purposeful, even though you know it is just physics, just magnetic fields and charged particles doing what physics demands. Several of the recordings made by spacecraft passing through the Jupiter system have been described by scientists as genuinely unsettling, not because they represent anything threatening directly, but because they remind you that you are inside the domain of something enormously powerful, something that fills the surrounding space with its presence even where you cannot directly see it. There is a phenomenon called the Jovian decametric radiation, radio emissions in the 10 to 40-meter wavelength range that bursts from Jupiter in powerful pulses correlated with the position of the Moon, Io. Io orbits inside Jupiter's radiation belts, and the material it ejects from its volcanoes, sulfur dioxide and other compounds, gets ionized and forms a plasma torus around Jupiter. This plasma torus interacts with Jupiter's magnetic field lines, and the result is electrical currents that flow between Io and Jupiter, carrying an estimated 5 trillion watts of power. 5 trillion watts. The entire electrical generating capacity of human civilization is roughly 25 trillion watts, so this single interaction between a moon and a planet carries a fifth of all the electrical power humanity produces continuously in the form of an invisible current flowing through space. This current generates radio emissions, and those emissions are powerful enough to interfere with Earth's radio telescope observations. They are detectable without specialized equipment under the right conditions. Jupiter is so loud in the radio spectrum that it is a nuisance to astronomers here on Earth, hundreds of millions of kilometers away. And Io, the moon responsible for part of this electrical drama, is a remarkable study in what it means to exist inside Jupiter's sphere of influence. Io is the most volcanically active body in the entire solar system. It is covered in volcanoes, hundreds of them, erupting continuously. The surface is constantly being reshaped by eruptions that send material hundreds of kilometers into space. The colors are extraordinary: orange and red and yellow and white, the products of sulfur compounds in various chemical states. Why is Io so volcanically active? Because of Jupiter, specifically because of tidal heating. Jupiter's immense gravity pulls on Io, and so does the gravity of the other large moons, Europa and Ganymede. These gravitational forces flex and squeeze Io as it orbits, and that flexing generates heat through friction in the interior. The heat has to go somewhere, and it goes out through volcanoes. Io is essentially being squeezed like a stress ball by Jupiter's gravity, and the heat from that squeezing powers the most intense volcanic activity in the solar system. Jupiter does not just affect Io, though. It affects all of its moons in profound ways. Europa, the icy moon that may harbor a subsurface liquid water ocean, has that ocean largely because of tidal heating from Jupiter's gravity. The same mechanism that makes Io volcanically active keeps Europa's interior warm enough that liquid water can persist beneath its icy crust. Ganymede, the largest moon in the solar system, larger than the planet Mercury, has its own magnetic field generated by the same basic mechanism that generates Jupiter's magnetic field, an electrically conducting liquid interior driven partly by tidal heating. The Jupiter system is not just a planet with moons. It is a miniature solar system in its own right, with complex gravitational and electromagnetic interactions between all of its components. Jupiter is simultaneously a planet orbiting the Sun and a kind of star at the center of its own small family of worlds, influencing and shaping, and in the case of Io, actively driving the geological processes of the bodies around it. And all of this influence, all of this power, all of this shaping of worlds comes from the same source that makes Jupiter so dangerous: its mass, its gravity, its enormous magnetic field. The same properties that make it a fascinating object to study are the properties that make it a hostile and violent place. We have been looking at Jupiter's surface, its atmosphere, its radiation environment, its influence on its moons. But we have not yet talked about the events that happen when Jupiter encounters things that get too close, the impact events, the moments when Jupiter's gravity catches something, and the result is spectacular in the way that only truly catastrophic events can be spectacular. In 1994, a comet called Shoemaker-Levy 9 collided with Jupiter. This was not a small impact. The comet had previously been captured by Jupiter's gravity and had been torn apart by tidal forces into a chain of 21 fragments, each ranging from a few hundred meters to perhaps 2 kilometers in diameter. Over the course of 6 days, in July 1994, these fragments fell into Jupiter one by one, each impact releasing energy equivalent to hundreds or thousands of nuclear weapons. The largest impact, from fragment G, released energy estimated at 600 times the world's total nuclear arsenal. It created a scar in Jupiter's atmosphere that was visible from Earth with amateur telescopes, a dark bruise larger than the entire Earth that persisted in Jupiter's cloud tops for weeks. 600 times the world's nuclear arsenal in a single impact, with one of 21 fragments of a single comet. The images of the Shoemaker-Levy 9 impacts are among the most dramatic ever taken of another planet in our solar system. Dark, roughly circular blotches spread across Jupiter's southern hemisphere like bruises. The plumes from the impacts rose thousands of kilometers above the cloud tops. The amount of material thrown up by the collisions was staggering. Scientists studying the aftermath found evidence of water and other compounds in Jupiter's upper atmosphere that had been dredged up from far below the normal cloud levels. Material that would otherwise take decades or centuries of gradual mixing to appear at those altitudes. And here is the thing about the Shoemaker-Levy 9 impacts that bears remembering. They happened in our lifetimes. They were predicted. They were observed. They were photographed with the best instruments available. They were, by any measure, one of the most significant astronomical events of the 20th century. And they left marks on Jupiter, marks larger than Earth, that faded over the course of weeks. Jupiter absorbed 21 comet fragments in 6 days, the largest of which released energy equivalent to 600 nuclear arsenals, and the visible evidence was gone within a few months. That is the scale of Jupiter. That is how vast and how energetic it is. Impacts that would sterilize an Earth-sized planet are, for Jupiter, merely temporary blemishes. The planet absorbs them, processes them, and moves on unchanged in any fundamental way. The scars fade because the atmosphere is so deep and so dynamic that the material from the impacts eventually gets mixed back into the vast planetary environment and distributed beyond detection. This is a useful thing to sit with. Jupiter absorbs impact events that would end all life on Earth, and they leave no lasting mark. The planet is so large, so energetic, so dynamic, that even apocalyptic collisions are trivial in the context of its overall existence. We are, by comparison, extraordinarily fragile. This fragility is something that becomes very apparent when you think about the relationship between what Jupiter is and what we are. We are biological creatures, evolved on a small rocky world, with a thin, protective atmosphere, a modest magnetic field, and a stable surface temperature range. Every aspect of our biology is calibrated to Earth. Our cells function within a narrow temperature range. Our bones can withstand a modest range of pressures. Our chemistry proceeds at atmospheric pressure and roughly room temperature. We are finely tuned instruments designed for exactly one environment, and that environment is nothing like Jupiter. The zone of habitability for life as we understand it does not include Jupiter in any meaningful way. Not the atmosphere, where the temperatures and pressures and chemical environment would destroy organic molecules. Not the deeper layers, where the conditions are more extreme still. Not the surface, because there is no surface. Not even the space around Jupiter, because the radiation belts would be lethal to anything resembling Earth life long before it got close to the planet itself. Jupiter is not just inhospitable. It is the opposite of hospitable in almost every measurable way. It is as different from Earth as it is possible for a body within our own solar system to be. And yet it is there, visible in our night sky, bright and serene looking, giving no outward sign of the extraordinary violence that defines it. That gap between appearance and reality is something worth dwelling on. When you look at Jupiter through even a modest backyard telescope, you see the bands, the cloud systems, the great red spot, if you catch it at the right time in its rotation. You see something beautiful, something intricate and patterned and almost orderly looking. The swirling clouds have a kind of aesthetic balance to them, a visual harmony that has made Jupiter one of the most photographed and admired objects in astronomical imaging. But what you are seeing is the surface expression of something violent. Those beautiful cloud bands are the tops of atmospheric columns that extend down into crushing pressure and unimaginable heat. The swirling patterns are the signature of winds that move faster than a rifle bullet and never stop. The great red spot, that elegant oval, is a storm system that has consumed smaller storms around it, absorbing them into its rotation, growing from the material it engulfs. It is not decorative. It is a cannibal. Over the past few decades of observations, astronomers have watched the great red spot slowly shrink. Measurements from the late 19th century suggested it was once perhaps 40,000 kilometers across. By the time the Voyager spacecraft flew past in 1979, it had shrunk to about 23,000 kilometers. By the early 2020s, it had shrunk to roughly 13 to 15,000 kilometers. It is still larger than Earth, but the trend is clear. What is happening to it? The storm appears to be losing material faster than it is gaining it. The complex interactions with the smaller storm systems that used to feed it have changed. There is speculation that the storm may eventually dissipate entirely, that the great red spot that has existed for at least 3.5 centuries may, on some astronomical timescale, finally die out. But here is the remarkable part. The storm is not going quietly. As it shrinks, it is intensifying. The wind speeds at its outer edges appear to have increased as the storm has gotten smaller and more compact. It is spinning faster as it gets smaller, concentrating its energy as its size decreases. The great red spot, even as it dies, is becoming more violent. It is going out like a whirlpool circling a drain, faster and faster as it contracts. And even if the great red spot does eventually dissipate, that will not make Jupiter's atmosphere calmer. It will simply mean that the energy currently concentrated in that one enormous feature will redistribute itself, potentially fueling other storm systems, adding to the general violence of the atmosphere. Jupiter does not have a calm mode. It does not have a gentle setting. The energy is always there, always being expressed, always generating turbulence and wind and weather on a planetary scale. This is the reality of the world we call our guardian. This is the planet we have named after the king of the Roman gods. Jupiter, the ruler of the heavens, the wielder of lightning. Ancient astronomers who named it did not know what they were naming, but they captured something true anyway. Jupiter rules the outer solar system through dominance, through mass, through the relentless expression of physical forces at a scale that dwarfs everything else around it. And we, looking up at it from our small rocky world, have had the luxury of admiring it from a distance. We have had the luxury of seeing the beauty in its clouds without experiencing the reality of what those clouds represent. We have been able to tell ourselves the comfortable story of the guardian planet, the helpful giant, the shield against cosmic danger. The truth is more interesting and more frightening than the comfortable story. The truth is that Jupiter is a world of permanent storms and lethal radiation and crushing pressure and temperatures that rival the surface of the Sun. The truth is that it nearly became a second star, and the near miss is the reason we exist. The truth is that its gravity has shaped the entire solar system through a combination of protection and violence, catching some things and flinging others, and it has never distinguished between the two. Jupiter does not protect us. Jupiter does what Jupiter does, and we are small enough and far enough away and lucky enough that we have mostly benefited from the side effects. That is not the same thing as being safe. Let us go deeper into the nature of Jupiter's winds, because the numbers we have discussed do not quite capture the full picture of what those winds actually are and what they actually do. On Earth, wind is fundamentally a surface phenomenon. It is air moving relative to the ground, driven by pressure differences that arise from temperature variations across the surface. A powerful thunderstorm produces winds of perhaps 200 kilometers per hour in extreme cases. A Category 5 hurricane might sustain winds of around 300 kilometers per hour at its most intense. These events are catastrophic. They destroy buildings, they level forests, they reshape coastlines, they kill people. Jupiter's atmosphere has no surface to interact with. The winds there are driven by a completely different set of mechanisms. The primary drivers are the planet's internal heat, rising upward from the still cooling interior, and the enormous Coriolis effect generated by Jupiter's rapid rotation. Remember that Jupiter completes one full rotation every 10 hours. For a planet with a circumference of nearly 450,000 kilometers at the equator, that rotation speed means the equatorial cloud tops are moving at roughly 45,000 kilometers per hour just from the rotation alone, before you add any wind speed on top of that. The Coriolis effect, the deflection of moving objects caused by a rotating planet, is responsible for the banded structure of Jupiter's atmosphere. On Earth, the Coriolis effect organizes large-scale weather patterns into recognizable features like trade winds and jet streams. On Jupiter, the same effect, amplified enormously by the faster rotation and larger scale, organizes the atmosphere into the alternating bands of east-flowing and west-flowing jets that we see in images. These jets are extraordinarily stable. Unlike Earth's jet streams, which migrate north and south with the seasons and can meander significantly, Jupiter's cloud bands have remained roughly consistent in their positions for centuries. They are a permanent structural feature of the planet's atmosphere. Within those bands, the wind speeds we discussed earlier, 500 to 600 kilometers per hour in the jets themselves, represent the sustained background. But superimposed on those background jets are smaller scale features, eddies and vortices and turbulent regions, where the local wind speeds can be even higher. The boundaries between adjacent bands, where east-flowing and west-flowing jets meet, are regions of intense shear. Two adjacent streams of gas moving in opposite directions, both at hundreds of kilometers per hour, creates a shearing interface that generates turbulence so violent it has no equivalent in any weather system on Earth. It is useful to try to visualize what that interface would look like if you could somehow be present at it. Two walls of gas, each moving at hundreds of kilometers per hour, but in opposite directions, meeting along a boundary that extends around the entire planet. The interface between them is not smooth. It generates vortices and turbulent structures that cascade in size from the scale of thousands of kilometers down to the scale of individual molecules. Energy flows from the large scales to the small scales in a cascade that dissipates heat continuously. The noise, if you could somehow hear it, would be deafening. But the most violent feature at those boundaries is not the turbulence itself. It is the storms. Small cyclones and anticyclones spin up at the shear interfaces, driven by the same dynamics that create storms along weather fronts on Earth, but at a scale and intensity that has no parallel in terrestrial weather. Most of these storms are small compared to Jupiter's scale, only a few thousand kilometers across, which makes them comparable in size to an entire continent on Earth. They form, evolve, and sometimes merge, and occasionally they encounter the Great Red Spot, which sits at one of these shear zones and has been feeding on smaller storms for potentially centuries. This feeding behavior is one of the stranger aspects of the Great Red Spot. Observations made over the past few decades have documented several instances of smaller storms being caught by the outer winds of the Great Red Spot and drawn into it, merged into the larger circulation. The storm does not simply exist in its location. It actively incorporates material from its surroundings. It grows from what it catches. Smaller storms that wander into its vicinity do not pass through. They are consumed. Their rotation is added to the larger system. This is partly why the storm has persisted for so long despite the various factors that should, by terrestrial storm logic, have caused it to dissipate. The Great Red Spot is not just a storm. It is a storm that eats other storms, a feature that sustains itself partly by incorporating the energy and rotation of smaller features that get too close. On Earth, we might call something like that an apex predator. In meteorology, the closest analogy might be a vortex that persists by continually absorbing fresh energy from its surroundings. But even that does not fully capture what the Great Red Spot is, because terrestrial storms do not have the persistence, the 300-plus year lifespan, or the sheer scale. Now let us talk about something that is perhaps the most philosophically unsettling aspect of Jupiter's atmospheric structure. The question of what is actually inside those beautiful bands, and what those colors mean in terms of the chemistry happening there. The bands we see in images of Jupiter are cloud layers, but the word cloud, with its comfortable associations of white fluffy things drifting overhead, does not quite prepare you for what Jupiter's clouds actually are. The uppermost cloud layer, the one we see in most images, is made primarily of ammonia ice crystals. Ammonia, the chemical compound that makes bleach and cleaning products smell sharp and harsh. In Jupiter's upper atmosphere, at temperatures of around minus 150 degrees Celsius, ammonia freezes into crystals that form clouds in the same way that water ice forms clouds on Earth. These ammonia ice clouds are the pale, cream-colored zones in Jupiter's band structure. Below that layer, where the temperature is slightly warmer, a different type of cloud forms. These are made of ammonium hydrosulfide, a compound formed when ammonia and hydrogen sulfide combine. The reddish-brown color of the dark belts in Jupiter's atmosphere comes largely from these ammonium hydrosulfide clouds, combined with complex organic molecules called chromophores, whose exact identity is still debated by scientists. Something in the chemistry of Jupiter's atmosphere produces these rich reddish and brownish colors, and while the specific molecules have not been definitively identified, the leading candidates include compounds formed when ultraviolet light from the sun reacts with simple molecules in the upper atmosphere, producing more complex organic chemistry in the clouds. And below the ammonium hydrosulfide layer, where the temperature climbs still further, a third cloud layer forms. This one is made of water ice and water droplets, similar to the clouds we have on Earth. In Jupiter's atmosphere, this water cloud layer sits deep enough that it is rarely directly visible from above. It is mostly hidden beneath the upper cloud decks. Below all three cloud layers, the atmosphere continues down into regions where no distinct clouds form, where the gas simply gets hotter and denser and more compressed, transitioning through liquid layers on its way to the metallic hydrogen region deep in the interior. The point of all this chemistry is that what looks like a beautiful, almost painted surface when you see Jupiter in images is actually a layered stack of chemical clouds, each made of a different compound, each existing at a different temperature and pressure, each expressing a different part of the complex chemistry happening in this enormous atmosphere. The beauty is real, the colors are real, but they are the colors of ammonia and sulfur compounds and organic molecules synthesized by ultraviolet radiation. They are not gentle colors. They are the colors of a chemistry that is alien to anything we encounter on Earth. The sulfur smell alone, if you could somehow translate Jupiter's chemistry into a sensory experience, would be overwhelming. Hydrogen sulfide is the compound responsible for the smell of rotten eggs. Jupiter's atmosphere contains substantial amounts of it. The ammonium hydrosulfide clouds, the ones responsible for the reddish-brown coloring of the dark belts, smell, to put it plainly, like a combination of ammonia and rotten eggs. If you could somehow bring a jar of Jupiter's upper atmosphere to Earth and open it, the smell would be intensely unpleasant. This is perhaps a small and somewhat absurd detail in the context of everything else that makes Jupiter lethal and hostile. The radiation would kill you long before you got close enough to smell anything. The pressure would destroy you long before any chemistry was relevant. But there is something about this detail. The fact that this planet of extraordinary and alien beauty smells like something deeply unpleasant, that captures the essential nature of Jupiter quite well. It is gorgeous from a safe distance. It is repellent on closer inspection. Let us now consider another dimension of Jupiter's violence that often goes overlooked in popular descriptions of the planet. The lightning. Jupiter has lightning. This is not surprising in itself, since lightning is a common feature of planetary atmospheres that contain clouds with the right charge separation mechanisms. Earth has lightning. So does Saturn. But Jupiter's lightning is different from ours in ways that are worth understanding. On Earth, lightning is generated in thunderstorm clouds through a process involving the collision of ice crystals and water droplets, which transfers electric charge between them. The result is a charge separation between the tops and bottoms of storm clouds, and when the voltage difference becomes large enough, a lightning bolt discharges and equalizes the charge. A typical Earth lightning bolt carries an energy of about 1 to 5 billion joules, which sounds like a lot until you realize it would only power a household for about a month. Jupiter's lightning bolts are incomparably more powerful. Based on measurements from the Galileo spacecraft and later from Juno, Jupiter's lightning bolts are estimated to be roughly 3 times more energetic than Earth's most powerful lightning, called superbolts, and about 1,000 times more energetic than typical Earth lightning. Some of the largest detected strikes release energies on the order of billions of joules per flash. And Jupiter has a lot of lightning. During Juno's close passes, the spacecraft detected hundreds of lightning events per pass, far more than was detected by earlier missions. The distribution of lightning is interesting too. On Earth, lightning is most common near the equator, where convection is strongest. On Jupiter, lightning is preferentially located at middle latitudes, near the transition zones between the equatorial region and the temperate zones, and at the poles. The equatorial region of Jupiter actually has relatively little lightning, which researchers believe is related to the dynamics of the atmospheric convection in those regions. The sound of Jupiter's lightning, converted from radio emissions to audio, has been recorded by multiple spacecraft. It has a distinctive low-frequency crackling quality, different from the sharp crack of terrestrial thunder. The emissions from Jupiter's lightning are detectable at radio wavelengths from Earth-based observatories. Jupiter's thunderstorms are, in a sense, broadcasting their existence across the solar system. There are regions of Jupiter's atmosphere that are permanently, continuously, extraordinarily violent with electrical activity. Thunderstorm systems that persist for months or years, generating lightning continuously, covering areas larger than entire continents, flashing thousands of times a day. From above, in the right wavelengths, these regions would look like Christmas lights visible from space. Constant flickering of enormous electrical discharges across thousands of kilometers of cloud. These thunderstorm systems are also among the most powerful sources of atmospheric uplift on Jupiter. The heat from the thunderstorm convection, the rising warm air that powers the lightning-generating clouds, is part of the mechanism that drives material upward from deeper layers of the atmosphere. This is how some of the deeper chemistry occasionally gets mixed into the upper layers, carried upward by the enormous convective plumes that fuel the thunderstorms. The storm systems are not just electrically violent. They are the mixing mechanisms of Jupiter's atmosphere, churning material from deep levels upward and spreading it through the cloud layers. All of these features, the winds, the banded structure, the great red spot, the lightning, the chemical clouds, are the outputs of a system that has been operating continuously for 4.5 billion years. Jupiter formed in the early solar system, and its atmosphere has been churning, mixing, and expressing its enormous internal energy ever since. The storm systems we see today are, in some sense, the same processes that have been running since the planet formed, evolved and changed over time, but continuous in their fundamental nature. Think about that persistence. 4.5 billion years of continuous atmospheric activity. Every storm we see on Jupiter today, every lightning bolt, every wind current, every chemical cloud, is part of a system that was already ancient when Earth was young. When the first life was emerging on Earth in the primordial oceans, when the first single-celled organisms were figuring out how to metabolize sunlight, Jupiter's atmosphere was already ancient. The Great Red Spot, if it has existed, as long as some researchers suspect, might have been spinning when the first complex multicellular life was evolving on Earth. This temporal scale, the sheer age and continuity of Jupiter's atmospheric processes, adds another dimension to the sense of scale that Jupiter evokes. It is not just physically vast, it is temporally vast. It operates on timescales that dwarf human civilization, human history, and most of the biological history of our planet. We are, in comparison to Jupiter, as brief and insubstantial as a single puff of smoke. We exist for eye blinks on the timescale that Jupiter's atmosphere operates on. Our entire recorded history from the first writing to the present day, is about 5,000 years. Jupiter's Great Red Spot has been spinning for at least 70 times that long. Our species has existed for perhaps 300,000 years, which is a small fraction of Jupiter's continuous atmospheric lifespan of 4.5 billion years. This is not a comfortable thought. It is, in fact, a thought that most of us avoid, because it implies something about our importance and our permanence that we would rather not confront. We build cities and nations and civilizations, and we think of them as lasting things, things that will endure. But in the context of Jupiter's temporal scale, even our geological record, the layer of sediments and fossils that will mark our existence in the rock for millions of years to come, is barely a rounding error. Jupiter simply does not register our existence. It has never registered the existence of anything on Earth. It predated life on Earth by a few 100 million years. It will outlast the Sun itself by eventually being ejected into the interstellar medium as the solar system dissolves over geological time, and it has never, in all of that vast span, done anything that could be described as awareness of our presence. This is what it means to say that Jupiter is not our protector. A protector is aware of what it protects. A protector makes choices. Jupiter makes no choices. It simply exists, governed by physics, influencing everything around it through gravity and radiation, and the relentless expression of its internal energy. It is the most powerful thing in the solar system after the Sun itself, and it is completely indifferent to everything. The word for what Jupiter is, stripped of all the comfortable mythology we have draped over it, is simply this: a force, not a guardian, not a monster, not really, because monsters have intention, just a force, enormous, ancient, continuous, indifferent. The largest expression of gravitational and atmospheric physics in our solar system, doing what physics demands, without variation, without pause, without any reference to the small rocky world, with thin oceans and fragile biology that sits a few 100 million kilometers closer to the Sun. We are the ones who decided to name it after a king. We are the ones who decided to see protection in its gravitational influence. We are the ones who decided to find beauty in its clouds. Jupiter had nothing to do with any of those decisions. It was busy doing what it has always done, stirring its atmosphere, radiating its internal heat, trapping particles in its magnetic field, and shaping the solar system through the simple and relentless fact of its enormous mass. The beauty is real, the scale is real, the violence is real, and the indifference is the most real thing of all. And so we arrive at a kind of pause in the story. We have walked through the myth and dismantled it. We have looked at the winds and the radiation, and the crushing pressure, and the chemistry that smells of sulfur, and the lightning that makes Earth storms look like sparks. We have looked at the Great Red Spot in its slow, intensifying death, spinning faster and smaller and more ferocious as it contracts. We have looked at the way Jupiter's gravity shaped the solar system, moving planets and preventing planets and scattering material across billions of kilometers. We have looked at what Jupiter nearly was and what that near miss cost and gave us. But we have not yet looked at the deepest layer of the story. We have not yet talked about what makes Jupiter not just dangerous, but strange, not just violent, but almost impossible to fully comprehend. We have not yet talked about what happens in the deepest interior, or about the moons that orbit in the grip of Jupiter's tidal forces, or about the full implications of the fact that this planet nearly became a second sun. Those pieces of the story come next, and they are, in some ways, the most remarkable pieces of all. Because the further in you go, the stranger it gets. There is a moon orbiting Jupiter that should not exist the way it does. It should be a quiet, cold, geologically dead world. It is the right size for that. It is the right age for that. By every standard rule of planetary science, a moon of its mass, at its distance from the Sun, having formed 4.5 billion years ago, should have exhausted its internal heat long ago. Its volcanoes should have gone cold. Its surface should be ancient and cratered and still. Instead, Io is the most volcanically violent place in the entire solar system. There are volcanoes on Io erupting right now, not metaphorically, not in a geological sense where right now means the last million years. Literally right now, as you read or listen to this, material is being ejected from Io's surface into space. The Voyager 1 spacecraft, passing through the Jupiter system in 1979, detected active volcanic plumes rising hundreds of kilometers above Io's surface. Scientists were stunned. They had not expected this. No one had expected this. A moon that small, that cold, that far from the Sun, should not have the internal energy to drive that kind of activity. The explanation, when it came, was both elegant and disturbing, because it pointed directly back to Jupiter and to the nature of gravitational forces at scales we do not experience in our daily lives. Io orbits Jupiter at a distance of roughly 422,000 kilometers, completing one orbit every 42 hours. But Io does not orbit alone. It orbits in a specific gravitational relationship with two other large moons, Europa and Ganymede. These three moons are locked in what is called an orbital resonance. For every one orbit Ganymede completes, Europa completes exactly 2 orbits, and Io completes exactly 4 orbits. They always return to the same relative positions at the same intervals. This regularity is not coincidental. It is maintained by the gravitational interactions between the moons themselves, a stable configuration that persists indefinitely. The consequence of this resonance is that Io's orbit is not a perfect circle. Every time Io comes close to Europa or Ganymede in its orbit, their gravity tugs on it slightly, distorting the orbit into a gentle ellipse. This means that as Io orbits Jupiter, its distance from the planet varies slightly. And because Jupiter's gravity at that distance is so enormously powerful, even a small variation in distance produces a significant change in the gravitational force Io experiences. Imagine squeezing a rubber ball. As you squeeze it, it deforms. When you release it, it springs back. The energy you put in through squeezing is released when it returns to its original shape. Now imagine that happening to an entire moon over and over with every orbit. Jupiter's gravity squeezes Io. As Io's orbit carries it slightly farther away, the squeezing relaxes. Then it comes close again, and the squeezing intensifies. The friction from this continuous flexing generates heat in Io's interior, and that heat has to go somewhere. It goes out through volcanoes, hundreds of them. The total heat output of Io from tidal heating is estimated at roughly 2 to 3 watts per square meter of surface area, which sounds modest until you multiply it across the entire surface of a moon the size of our own moon. The total power output from Io's tidal heating is roughly twice the total power consumption of human civilization. Jupiter is squeezing a moon with a force equivalent to twice all of humanity's energy use, continuously, and the result is a world that looks like a pizza left under a broiler. The surface of Io is covered in volcanic plains, lava, lakes, calderas, and eruption plumes. The colors range from bright yellow to deep red, to white to black, depending on the sulfur compounds deposited by volcanic activity. There is almost no water on Io. Any water that was there has long since been driven off by the intense heat. Instead, the surface is a mosaic of solidified sulfur and silicate rock, constantly being resurfaced by new eruptions so active that impact craters, which cover most solid bodies in the solar system, are almost completely absent. By the time an impact crater forms on Io, new volcanic deposits have buried it. The volcanoes themselves are extraordinary. The largest volcanic feature on Io is called Loki Patera, a lava lake roughly 200 kilometers across, making it larger than the state of Kentucky. It erupts periodically in a pattern that suggests a wave of overturning lava periodically sweeps around its surface as the dense cooled crust sinks and hot fresh lava wells up from below. The Pele volcano generates eruption plumes that rise 300 kilometers above the surface and spread sulfur dioxide deposits over an area larger than Alaska. And all of this, every eruption, every lava lake, every plume, is a direct consequence of Jupiter. Without Jupiter's gravitational squeeze, Io would be a cold, dead world. With it, Io is the most volcanically active body we have ever found. Jupiter has essentially turned a moon into a geological engine, powering it continuously through the simple mechanism of its own overwhelming gravity. But while Io's relationship with Jupiter is spectacular, it is Europa's relationship with Jupiter that is, in some ways, more significant for the question of life in the universe. Europa is covered in ice. Smooth, bright, fractured ice that reflects sunlight so effectively that Europa is one of the brightest objects in the solar system relative to its size. The surface is cold, roughly minus 160 degrees Celsius, and it is laced with a network of long, reddish-brown lines and ridges that crisscross the surface like cracks in a frozen lake, which is exactly what they are. Beneath Europa's icy surface, there is liquid water, an enormous global ocean, completely covered by the ice shell, dark and cold, and hidden from any sunlight. This ocean is estimated to be between 60 and 150 kilometers deep, containing roughly twice as much liquid water as all of Earth's oceans combined. It has probably been liquid for most of the solar system's history, kept from freezing by the same tidal heating that powers Io's volcanoes, though in Europa's case, the heating is gentler, and the result is a liquid water ocean rather than volcanic eruptions. The existence of this ocean changes the calculation about life in the solar system dramatically. For decades, scientists assumed that life required sunlight. The habitable zone concept is built around proximity to a star, but we know from discoveries in Earth's own deep oceans that life does not require sunlight. Chemosynthetic ecosystems built around hydrothermal vents on the ocean floor exist in complete darkness, deriving energy from chemical reactions rather than from sunlight. These ecosystems are rich and diverse. They include bacteria, tube worms, shrimp, crabs, and numerous other organisms. If the same process operates on Europa, if tidal heating warms Europa's rocky sea floor and drives hydrothermal activity, then Europa's subsurface ocean might have all the ingredients for life: liquid water, chemical energy from hydrothermal vents, the basic organic molecules that chemistry produces when the right elements are combined. None of it requires sunlight. None of it requires proximity to a star. And here is the extraordinary part. This potential for life in Europa's ocean exists entirely because of Jupiter. The same tidal forces that make Io a volcanic nightmare keep Europa's ocean liquid. Without Jupiter, Europa would be a frozen ball of ice, completely solid, lifeless. With Jupiter, it might harbor an ocean that has been continuously liquid for billions of years, longer than complex multicellular life has existed on Earth. Jupiter, the planet we have been describing as a monster, as a force of violence and destruction, is also, through the precise same mechanism of its overwhelming gravity, potentially the creator of conditions for life, not on its own surface, which is completely and utterly inhospitable to any life we can imagine, but on one of its moons, hidden beneath kilometers of ice, in a dark ocean warmed by the tidal squeeze of Jupiter's gravity. The universe's most violent planet in our solar system may be the guardian of life after all, just not in the way we thought, and not for the reasons we told ourselves, not by deflecting asteroids, not by acting as a shield, but by squeezing a moon with enough gentle force to keep an ocean warm in the frozen outer solar system. This duality is one of the most striking things about Jupiter. Everything it does at an extreme. Its violence is extreme. Its influence is extreme. Its beauty is extreme. And even its potential role in the story of life, if Europa does harbor biology, would be extreme in its way, an ocean created not by proximity to a star, but by the tidal grip of a gas giant. The NASA Europa Clipper mission, launched in October of 2024, is currently on its way to the Jupiter system, specifically to study Europa in detail. It will not be able to directly sample the subsurface ocean. The ice shell is too thick for any current penetration technology. But it will characterize the ice shell, measure the ocean's properties through magnetic and gravity measurements, look for plumes of water vapor that might be venting from the surface, and try to determine whether the chemical conditions in the ocean are compatible with life as we understand it. The results of that mission, expected to begin arriving from the Jupiter system in the early 2030s, could fundamentally change our understanding of where life can exist in the universe. And all of it, every discovery that mission makes, every data point about Europa's ocean, will trace back to Jupiter, to the violence of Jupiter's gravity, to the relentless tidal squeeze that has been warming Europa's interior for billions of years. Now let us go inside Jupiter, not just to the cloud layers, not just to the crushing pressure region, but all the way to the core. Because the interior of Jupiter is where the story gets strangest, and where the implications for understanding what planets are and what they can become are most profound. We know a great deal about Jupiter's interior from indirect measurements. Spacecraft in orbit around Jupiter can measure tiny variations in the planet's gravitational field, and those variations tell us something about the distribution of mass inside the planet. The way Jupiter's gravity pulls on orbiting spacecraft differently at different positions reveals information about the layers within. The Juno mission has provided the most detailed gravitational field measurements ever made of Jupiter, and the results have been genuinely surprising. Earlier models of Jupiter's interior imagined a relatively clear structure, a rocky or icy core surrounded by liquid metallic hydrogen, surrounded by an outer layer of liquid hydrogen and helium, topped by the gaseous atmosphere we can see. Clean layers, distinct boundaries. The data from Juno tells a more complicated story. The core of Jupiter appears to be diffuse, not a compact, well-defined rocky ball at the center, but a fuzzy region of heavy elements, rocks and ices mixed in with the metallic hydrogen, spread over a larger volume than expected. Some models suggest the core might actually extend roughly halfway out to Jupiter's surface by radius, which would make it an enormous region of mixed composition rather than a compact central nucleus. One explanation for this diffuse core is that Jupiter experienced a giant impact event early in its history. Another large protoplanet, perhaps 10 times the mass of Earth, may have collided with the young Jupiter and disrupted its core, spreading the heavy material that had concentrated at the center outward into the surrounding hydrogen. If this happened, and the gravitational field data is consistent with it having happened, then Jupiter's interior has been slowly trying to resettle ever since, the heavy material gradually sinking back toward the center through a process that would take billions of years to complete. Under this scenario, Jupiter's interior is still mixing, still recovering from a collision that happened billions of years ago. The planet we see today is still, in a geophysical sense, reverberating from an ancient impact. This possibility, that Jupiter was hit by a massive impactor early in its history and has been recovering for billions of years, adds yet another dimension to the violence that characterizes this planet. Even its interior history was shaped by catastrophe. Below the diffuse core region, the liquid metallic hydrogen layer dominates. This is the material we discussed earlier, the electrically conducting form of hydrogen that generates Jupiter's magnetic field. But even within the metallic hydrogen layer, the Juno data has revealed unexpected complexity. The boundary between the metallic hydrogen layer and the outer molecular hydrogen layer is not sharp. There is a transition zone where the properties of the hydrogen change gradually rather than abruptly, and the details of how this transition happens affect the dynamics of the magnetic field. Jupiter's magnetic field, already known to be vastly more powerful than Earth's, turns out to be even more complex in its structure than earlier measurements suggested. It has multiple poles, not just a north pole and a south pole, the way Earth's magnetic field is organized, but a more complicated multipole structure with regions of unusually intense field concentrated near specific locations. Near the equator, there is a band of intense magnetic field. Near the South Pole, there is another concentrated region. This complex structure reflects the complex dynamics of the liquid metallic hydrogen dynamo in the interior, driven by convection and rotation in ways that Earth's magnetic dynamo, liquid iron in the outer core, does not replicate. The complexity of Jupiter's magnetic field has practical consequences for everything that orbits within it. The radiation belts, already the most intense in the solar system, have a complex spatial structure that reflects the multipole magnetic topology. Some regions within the Jupiter system are more intensely irradiated than others in ways that are difficult to predict without detailed magnetic field models. The charged particles trapped by the magnetic field are concentrated into specific regions by the field structure, and anything orbiting in those regions receives correspondingly intense radiation doses. The interaction between Jupiter's magnetic field and the Sun's magnetic field, the solar wind, is also different from the interaction at Earth. At Earth, the solar wind compresses the magnetosphere on the sunward side and stretches it out into a long tail on the opposite side. At Jupiter, the same basic geometry applies, but the scale is so much larger that the dynamics are different. Jupiter's magnetosphere extends roughly 60 to 90 Jupiter radii toward the Sun and trails out to hundreds of Jupiter radii in the opposite direction. This magnetotail, the elongated part of the magnetosphere on the side away from the Sun, is wide enough that Saturn's orbit occasionally passes through it during certain periods of the planet's relative positions. Think about what that means. Jupiter's magnetic influence extends far enough that it can encompass another planet. Saturn, a gas giant in its own right, capable of stunning complexity and beauty, occasionally finds itself within Jupiter's magnetic domain. In the scale of the solar system, This is extraordinary. And yet Jupiter's influence extends even beyond its magnetosphere, in another sense. The gravitational influence of Jupiter reaches throughout the solar system. The asteroid belt exists in its current form because of Jupiter. The Trojan asteroids, two large groups of asteroids that orbit at the same distance from the Sun as Jupiter, but 60 degrees ahead of and behind it in its orbit, are trapped there by the combined gravitational influence of Jupiter and the Sun. There are currently known to be more than 10,000 asteroids in the Trojan groups, and the actual population is much larger than what has been catalogued. The Trojans are a permanent legacy of Jupiter's gravitational dominance. They have been in those stable positions for billions of years, swept up and trapped there during the early solar system, maintained in their positions by the gravitational balance between Jupiter and the Sun. They are, in a real sense, Jupiter's debris, the residue of its gravitational influence on the material of the early solar system. Beyond the Trojans, Jupiter's gravitational resonances extend their influence throughout the outer solar system. The Kirkwood gaps in the asteroid belt, regions where there are notably fewer asteroids than at other distances from the Sun, are caused by gravitational resonances with Jupiter. Objects in those gaps experience repeated gravitational tugs from Jupiter at the same point in their orbits, and over time these tugs destabilize the orbits and scatter the objects out of the gap. The gaps are maintained continuously. Any asteroid that drifts into a resonant gap location is eventually scattered out by Jupiter's repeated gravitational nudges. This is the full picture of Jupiter's gravitational influence. Not just the immediate vicinity of the planet, not just the radiation belts and the tidal heating of the moons, but a gravitational fingerprint that extends throughout the solar system, sculpting the distribution of small bodies, maintaining the Trojans in their orbits, clearing the Kirkwood gaps, and in the distant past, driving the Grand Tack migration that reshaped the architecture of the inner solar system. Jupiter has been the dominant gravitational influence in the solar system for 4.5 billion years, second only to the Sun itself, and it has shaped everything. Every planet's orbit has been influenced by Jupiter. Every asteroid's position reflects Jupiter's gravitational history. The distribution of water in the inner solar system, the delivery of organic molecules to early Earth, the character of the late heavy bombardment, all of it connects back to Jupiter. We live on a planet that exists in its current form, partly because of what Jupiter did. Earth's oceans might have been delivered by comets and asteroids kicked inward by Jupiter's gravitational influence. The raw materials for our biology might have arrived on the early Earth, riding on impactors whose orbits were shaped by Jupiter. In a very literal sense, some of the atoms in your body may have arrived on Earth because Jupiter directed the object that carried them here. The king of the solar system, the planet that rules through violence, may have also been the unconscious agent of life's emergence. Not by protecting us, not by shielding us, but by stirring the solar system so thoroughly that the ingredients for life were mixed and delivered to the right place at the right time. This is the paradox of Jupiter. It is simultaneously the most destructive and the most creative force in the solar system outside of the Sun. Its gravity shatters and scatters. Its gravity also warms and delivers. Its tidal forces make Io a volcano-covered hellscape. Its tidal forces also keep Europa's ocean liquid. Its gravitational migrations during the early solar system disrupted the formation of planets in the inner solar system. Those same migrations may have delivered the water and organics that eventually gave rise to life on Earth. Jupiter does not choose between these roles. It simply exists, and the outcomes of its existence are simultaneously terrible and generative, destructive and creative, in the way that all truly powerful forces tend to be. Now let us come back to that near miss. The question of what Jupiter almost was, and what it means that it fell short. We established earlier that Jupiter would need to be about 80 times more massive to ignite sustained hydrogen fusion and become a true star. We established that the lower mass limit for a brown dwarf is about 13 times Jupiter's current mass. But there is another class of object worth knowing about, one that blurs the line between planet and star even further. Brown dwarfs more massive than about 65 Jupiter masses can ignite a form of nuclear fusion involving the element lithium, burning the lithium in their cores for a limited period before it is exhausted. Below that mass threshold, no nuclear burning of any kind occurs, and the object simply cools slowly over billions of years, becoming dimmer and dimmer until it eventually becomes something dark and cold and nearly undetectable. Jupiter, at 1 Jupiter mass, is obviously well below all of these thresholds. It does not fuse hydrogen. It does not fuse deuterium. It does not fuse lithium. It simply compresses its own interior through gravitational contraction, generating heat as it slowly shrinks and radiates that heat away into space. But here is something that is not often discussed in casual descriptions of Jupiter. Despite not being a star, Jupiter is doing something that is qualitatively similar to what stars do. It is radiating more energy than it receives from the Sun. The total power output of Jupiter, including the heat it radiates from its own slow contraction, is roughly 1.5 times the power it receives as sunlight. Jupiter is generating its own energy and releasing it, not through nuclear fusion, not at the scale of a star, but through the same basic mechanism of gravitational compression that powered the very early Sun before nuclear fusion ignited. The young Sun, in the earliest stages of its formation before its core became hot and dense enough to sustain fusion, was powered by gravitational contraction in exactly the way Jupiter is still powered today. Jupiter is, in this sense, frozen in an early stage of stellar evolution. It got as far as gravitational contraction but never reached fusion ignition. It is a planet that operates on a stellar mechanism, just at a completely insufficient scale to achieve what stars achieve. This adds a strange note to Jupiter's character. It is not quite a planet in the way that Earth is a planet. It has no solid surface, no defined boundary, no clear distinction between interior and exterior. It generates its own heat like a star. Its magnetic field is generated by a mechanism similar to what operates inside stars. It has a system of moons that orbit it like planets orbit a star. In many ways, Jupiter is a miniature solar system rather than simply a planet. Some astronomers have argued that the distinction between a large gas giant and a small star is somewhat arbitrary, that the universe produces objects on a continuous spectrum from small rocky planets through gas giants, through brown dwarfs to stars, and that Jupiter sits somewhere on that spectrum closer to the stellar end than the rocky planetary end. Not a star, but not quite a planet, in the way we usually use that word. Something in between, something the universe produces abundantly in other solar systems, but which exists in our own solar system in just one example. The exception that sits at the edge of what planets can be. If Jupiter had formed with just 13 times more material, it would have crossed into brown dwarf territory, 13 times more. In a solar system that produced a sun containing 330,000 Earth masses of material, The difference between Jupiter the gas giant and Jupiter the brown dwarf is a relatively small fraction of the total material budget. In other star systems, we find gas giant planets many times Jupiter's mass, superjupiters, objects so massive they blur the line with brown dwarfs. We find them orbiting close to their stars in short-period orbits that leave the inner system hostile to rocky planet formation. We find them in wide orbits that do not allow for stable habitable zones. The solar systems built around superjupiters are by and large not the kind of solar systems that produce Earths. The gravitational dominance is too extreme, the architecture too disrupted. Our Jupiter is, in a cosmological sense, relatively mild. A one Jupiter mass planet in a long orbit that leaves the inner solar system mostly stable. A gas giant that is dominant but not overwhelmingly so. A planet whose gravitational influence is enormous, but which stops short of the kind of extreme disruption that makes inner rocky planets and habitable zones unlikely. We got lucky with the size of Jupiter, just as we got lucky with its orbit, just as we got lucky with the timing of its formation and migration. The solar system's architecture, the set of coincidences that produced a stable habitable zone with a rocky planet in it, is a chain of lucky outcomes, and Jupiter's precise mass is one of the links in that chain. 13 times more mass, and we might not be here. 13 times less mass, and Jupiter's gravitational influence might have been insufficient to sculpt the asteroid belt the way it did, might have left more debris in the inner solar system, might have led to more frequent large impacts on early Earth. The window within which Jupiter's mass is beneficial to our existence is not an enormous one. We exist because Jupiter is exactly the size it is, and Jupiter has no idea. Let us now look at what Jupiter represents in the broader context of what we are learning about planetary systems throughout the galaxy. Because the perspective from exoplanet science, from the study of planets orbiting other stars, changes how we see Jupiter in important ways. In the first few decades of exoplanet detection, the most commonly found planets were hot Jupiters, gas giants orbiting very close to their host stars. They were easiest to find because their large size and close orbits made them detectable with early techniques. But as detection methods improved, and we became able to find smaller and more distant planets, the picture changed. We found that hot Jupiters are actually relatively rare. Most planetary systems do not have a gas giant close to their star, and systems that have a gas giant in a Jupiter-like long orbit are also not especially common. The solar system's architecture, with small, rocky inner planets and gas giants in the outer system, is not the most common arrangement we find. Many planetary systems have their largest planets in short orbits, or have no gas giants at all, or have multiple gas giants in complex orbital configurations. Systems that look like ours, with an outer gas giant leaving a clear, stable inner system for rocky planets, are a specific type. This specificity matters for the question of life. If Jupiter-like configurations are relatively uncommon, and if such configurations are necessary, or at least helpful for producing stable rocky planets with long-term habitable conditions, then the conditions for complex life might be rarer than a simple counting of rocky planets in habitable zones would suggest. The presence of a Jupiter-like planet in the right location and the right mass is part of the recipe. We do not know yet what fraction of planetary systems with Jupiter analogues also harbor rocky planets with life. We do not even know whether Jupiter is necessary for life on Earth, or merely one of several contributing factors. But the question is a live one in astrobiology, and the answer will shape our understanding of how common or rare Earth-like situations are in the galaxy. Jupiter is, from this perspective, not just a feature of our solar system, but a data point in one of the deepest questions we can ask. Are we common or are we rare? Does life permeate the galaxy, or are we an unusual outcome? Jupiter's precise mass, its orbital position, its timing of formation and migration, all of these contribute to the answer. The monster planet that rules our outer solar system through violence and indifference is also potentially one of the reasons we exist to ask these questions. This is the strange loop at the center of Jupiter's story. The most dangerous thing in the solar system is also, possibly, one of the necessary conditions for our being here to find it dangerous. There is something deeply humbling about this. We stand on our small rocky world and we look up at Jupiter, this beautiful and terrifying presence in the night sky, and we know now what it actually is. We know about the winds that never stop. We know about the radiation that would kill us before we could get close. We know about the pressure that would dissolve a diamond. We know about the near miss with stellar ignition. We know about the tidal violence it inflicts on its moons. We know about the way it has shaped the entire solar system through the relentless expression of its gravitational dominance. And we also know, now, that some of the atoms in our bodies may have arrived on Earth because of Jupiter, that the water in our oceans may be there partly because of Jupiter, that the stable orbit we enjoy, the orbit that has allowed Earth to maintain liquid water and a stable climate for billions of years, is partly a consequence of Jupiter's gravitational influence on the solar system's architecture. Jupiter did not intend any of this. It did not protect us in the sense of choosing to protect us. It did not provide us with water and organic molecules in the sense of making a choice to give us gifts. It simply existed, as it has always existed, as an enormous ball of gas and liquid and exotic matter, doing exactly what physics demands it do. The consequences of its existence, both the violent and the generative ones, are the unavoidable outcomes of having something that massive in the solar system. But the consequences are real, and we are among them. This is perhaps the most fitting summary of what Jupiter is. Not a guardian, not a monster, not a failed star or a near miss or a cosmic accident, though it is all of these things in different senses. Jupiter is a consequence of the solar system's formation, and we are a consequence of Jupiter's existence, and the chain of causes and effects that connects the formation of a gas giant 4.5 billion years ago to the emergence of life on a small rocky planet in the inner system is one of the most extraordinary stories that physics has ever told. We named it after the king of the gods. We did not know how apt that was. Jupiter rules not through intention, but through sheer overwhelming presence. It shapes everything around it through the simple fact of its existence. It creates and destroys without preference. It has presided over the solar system for as long as the solar system has existed, and it will continue to do so long after the sun expands into a red giant and the inner planets are swallowed. In the very long run, as the sun evolves and eventually dies, the outer solar system will be disrupted. The planets may be scattered. Jupiter itself may eventually be expelled from the solar system entirely as the sun loses mass in its final stages and the gravitational bonds that hold the system together begin to weaken. Jupiter may spend its final billions of years drifting through interstellar space, a cold and dark wanderer, still churning its atmosphere, still radiating its internal heat, but orbiting nothing, belonging to nothing, simply moving through the galaxy until whatever comes next. Or it may be consumed by the expanding sun. It is not certain which outcome awaits it, and the timescales involved are so vast that it barely seems worth worrying about. The Sun will not begin its red giant phase for another 5 billion years or so. On that timescale, everything we know will have changed beyond recognition many times over. But the fact that even Jupiter's story has an ending, that even this enormous and ancient and overwhelming presence in the sky is temporary on long enough timescales, is its own kind of reflection on the nature of things. Nothing in the universe is permanent. Not the Sun, not the solar system, not Jupiter. The forces that created Jupiter will eventually, in a different form, unmake it. For now, though, for the eye blink of geological time in which we exist, Jupiter is there. Enormous, ancient, beautiful, violent, indifferent. Spinning, once every 10 hours at the center of its own miniature system of worlds. Radiating heat generated by its own slow contraction. Generating radio emissions loud enough to be heard across the solar system. Squeezing its inner moons with a tidal grip that keeps oceans liquid beneath kilometers of ice. Dominating the gravitational landscape of the outer solar system with the simple, overwhelming fact of its mass. We spend a lot of time looking outward, past Jupiter, toward the distant stars and the possibilities of other solar systems and other worlds. And there is good reason to look outward. The universe is vast and full of remarkable things, but sometimes it is worth pausing and looking at what is already here, in our own solar system, already extraordinary, already beyond easy comprehension. Jupiter has been in our sky for as long as there have been eyes to see it. Every civilization in human history has looked up and seen that bright, steady light, moving slowly against the stars. None of them knew what it really was. We are among the first humans in all of history who do know. We have sent spacecraft to orbit it and plunge into it. We have measured its magnetic field and its radiation belts and its storm systems. We have watched comets fall into it and leave marks larger than our whole planet. We have found evidence for oceans beneath the ice of its moons. We have traced the history of its formation and migration and gravitational influence. And what we have found is not the guardian we imagined. What we have found is something stranger and more magnificent and more terrifying and more important than the simple story we used to tell. What we have found is the king of our solar system. A world that rules through mass and gravity and the relentless expression of physical law. A beautiful monster. A cosmic near miss. A force that has shaped everything, including, in its own indirect and unintentional way, us. The next time you look up and find that bright, steady point of light in the night sky, the one that does not twinkle the way stars do, the one that moves slowly against the background over the course of weeks and months, think about what you are actually seeing. Not a distant light, not a friendly guardian, not a safe and peaceful giant. You are looking at a world of permanent hurricanes larger than Earth. You are looking at a storm that has been consuming other storms for centuries. You are looking at radiation belts that would kill you before you could get close. You are looking at pressure that would dissolve a diamond. You are looking at a world where it may rain diamonds in the deep interior. You are looking at the strongest magnetic field of any planet in the solar system. You are looking at a world that nearly became a second sun and stopped just barely short of ignition. You are looking at the thing that shaped the asteroid belt and possibly delivered Earth's water and has been the gravitational anchor of the entire solar system for 4.5 billion years. You are looking at Jupiter. And Jupiter, as always, is not looking back. It does not need to. It never has. It just exists. And that, in the end, is exactly what makes it so extraordinary. Not its awareness, not its intention, simply its existence. The fact that something so enormous and so powerful and so complex and so ancient is simply there in our sky, real and present, and completely beyond anything our small bodies and brief lives can fully encompass. Astronomy is full of moments like this. Moments where the universe reveals something that makes you feel very small and very brief, and very lucky to be here at all. Jupiter is one of the most powerful of those moments, because unlike distant galaxies and abstract black holes and theoretical quantum phenomena, Jupiter is right here, in our own solar system, visible to the naked eye, measurable and explorable and real in the most immediate way. And it is still, even after centuries of observation and decades of spacecraft exploration, still capable of surprising us, still revealing new complexity in its magnetic field and its core structure and its storm systems and its interactions with its moons. We have been learning about Jupiter for nearly 400 years since Galileo first pointed a telescope at it and saw the 4 large moons. We will be learning about it for centuries more, and each time we look closer, we find something unexpected, something that reminds us that the universe does not run out of complexity at any scale, that even a planet in our own solar system, something we have observed for nearly as long as we have had science, still contains depths we have not fully plumbed. That is the gift that Jupiter gives us, if we want to call anything about it a gift, not protection, not safety, but wonder. The continuous reminder that the universe is larger and stranger and more various than we know. That the comfortable stories we tell ourselves about the cosmos are always simplifications of something richer, that there is always more. Jupiter is the king of our solar system. And like all great kings in all the old stories, it rules not through kindness, but through power. Not through love, but through dominance. Not through choice, but through nature. It is a beautiful monster. It has always been a beautiful monster, and it will be a beautiful monster long after we are gone. If you have spent this time with Jupiter and felt something shift in the way you see the night sky, something small but real, a little of the comfortable distance falling away and the actual scale of things pressing closer, then you have felt what space science feels like when it works. Not the comfortable version, the real version. The one where the universe is not arranged for your safety or your comfort, but is simply what it is, vast and ancient and operating by rules that do not include us in their calculations. That feeling is not fear, exactly. It is closer to awe. The specific kind of awe that comes from understanding something about the scale of existence that your body and your daily life were never designed to accommodate. The kind of awe that opens something up, rather than closing it down. Jupiter is out there right now, spinning, storming, squeezing its moons, dominating its little corner of the solar system with mass and gravity and electromagnetic fury. It does not know you are thinking about it. It does not know you exist. It has never known anything in the 4.5 billion years of its existence. And yet, here you are, a brief and improbable product of the same solar system that produced Jupiter, thinking about it, understanding it, finding it beautiful and terrifying and extraordinary. That is something Jupiter cannot do, and you can. That is the thing we have that the king of our solar system does not. Go look for it in the sky tonight, if the sky is clear. Find that bright, steady light that does not twinkle, and know, really know, what you are looking at. Let us take one more careful look at something that deserves more attention than it usually gets in discussions of Jupiter, the moons. Not just Io and Europa, which we have already explored, but the full sweep of what orbits Jupiter, because the Moon system is itself a kind of testament to the scale of what Jupiter is and what it does. Jupiter has 95 known moons as of recent counts, 95 individual bodies orbiting a single planet. The smallest are tiny, irregular rocks captured from the asteroid belt or the Kuiper belt, some only a kilometer or two across, orbiting in distant inclined orbits that take years to complete. The largest, the 4 moons that Galileo discovered in 1610 with his early telescope, are worlds in their own right. Ganymede, the largest of Jupiter's moons and the largest moon in the solar system, is bigger than the planet Mercury. It is bigger than Mercury in both size and volume, though Mercury is denser and therefore more massive. Ganymede has its own magnetic field, the only moon in the solar system known to do so, generated by convection in its liquid iron core. This magnetic field creates a small magnetosphere nested inside Jupiter's enormous magnetosphere, a bubble of Ganymede's own magnetic influence embedded within the vast magnetic domain of its parent planet. The interaction between Ganymede's magnetosphere and Jupiter's magnetosphere produces auroras on Ganymede. Glowing bands of light near Ganymede's polar regions, caused by charged particles being directed by the intersecting magnetic field lines. The Hubble Space Telescope has imaged these auroras. They shift position as Jupiter's enormous magnetic field rocks back and forth relative to Ganymede's smaller one, and measuring those shifts is one of the ways scientists have confirmed that Ganymede also harbors a subsurface ocean, because the ocean affects how Ganymede's magnetic field responds to Jupiter's influence. So Ganymede, like Europa, may have a liquid water ocean beneath its ice and rock surface. The ocean is deeper in Ganymede's interior, sandwiched between layers of ice, but the magnetic field measurements suggest it is there. If confirmed, it would mean that at least 2 of Jupiter's 4 large moons have subsurface liquid water oceans, possibly 3, because even Callisto, the outermost and most heavily cratered of the 4, shows some magnetic evidence consistent with a subsurface ocean. 3 moons with subsurface oceans, all orbiting the same planet, all kept potentially habitable by the same planetary system's gravitational dynamics. The solar system we live in contains, as far as we currently know, 1 world with life on its surface. It may also contain 3 worlds with potentially habitable conditions beneath their surfaces, all orbiting Jupiter. This is a remarkable thing to know. It means that when we talk about the possibility of life in the solar system, we are not just talking about Mars and its ancient riverbeds. We are talking about the moons of Jupiter, worlds that exist in permanent shadow under kilometers of ice, warmed by tidal forces rather than sunlight, containing more liquid water in total than all of Earth's oceans many times over. The entire question of whether life requires proximity to a star, which dominated thinking about astrobiology for decades, has been complicated enormously by what we have learned about Jupiter's moons. Life as we know it emerged on a sunlit world, but life as it might exist has a much wider range of possible homes, and several of those possible homes are orbiting the most violent planet in our solar system. Callisto deserves a moment of attention too, because it is in its own way a remarkable object, where Io is continuously resurfaced by volcanic activity and Europa's ice is constantly refreshed by tidal forces. Callisto is the opposite. Callisto's surface is the most heavily cratered surface in the solar system. It is ancient beyond easy description, a battered record of every impact it has suffered since the early solar system. It has not been significantly geologically active for billions of years. Its surface preserves a history of bombardment that has been erased from every other world in the inner solar system and from most of the outer ones. In some sense, Callisto is what Jupiter's moons might look like without the extraordinary tidal heating dynamics. It orbits far enough from Jupiter that the tidal squeeze is much weaker, and the result is a world frozen in time, its surface a museum of early solar system violence. The contrast with Io is almost surreal. One orbit closer, and you have the most volcanically active body in the solar system, continuously resurfaced, covered in fresh material, its ancient craters completely buried. One orbit farther, and you have the most cratered surface in the solar system, unchanged for billions of years, a perfect record of ancient bombardment preserved in ice and rock. Jupiter's gradient of tidal influence is so steep, so rapidly varying with distance, that its innermost large moon and its outermost large moon exist in completely different geological regimes. Io is a living, erupting world. Callisto is a fossil. And between them, Europa and Ganymede occupy intermediate positions, geologically active enough to maintain liquid water oceans, but not so violent as to be completely resurfaced. This gradient is itself an expression of Jupiter's fundamental nature. Everything in Jupiter's vicinity is shaped by Jupiter's gravity, but the shaping is not uniform. It varies with distance in a way that produces a spectrum of geological outcomes, from the extreme volcanic activity of Io to the frozen immobility of Callisto. Jupiter's influence is simultaneously the source of some of the most geologically active environments in the solar system, and some of the most geologically dead. Now let us talk about something that requires a slight shift in perspective. We have been discussing Jupiter's relationship with the rest of the solar system, its influence on its moons, its gravitational sculpting of the asteroid belt, its role in the Grand Tack migration. But there is another dimension to Jupiter's place in the solar system that is worth examining. The question of how Jupiter interacts with the Sun itself. Jupiter and the Sun do not simply orbit each other in the simple way that we usually describe. The Sun does not sit perfectly still while Jupiter orbits it. In reality, both the Sun and Jupiter orbit their common center of mass, the point at which their combined gravitational influence is balanced. This center of mass, called the barycenter of the Jupiter-Sun system, lies just outside the surface of the Sun, roughly 1 million kilometers from the Sun's center. Because Jupiter is so massive, the center of mass of the solar system is not inside the Sun. It is just outside it. This means the Sun itself wobbles, describing a small orbit around this point as Jupiter moves around it. The wobble is small by cosmic standards, less than the Sun's own diameter, but it is measurable, and it is the same effect that we use to detect planets around other stars. When we see a distant star wobbling slightly in a periodic way, we infer that a large planet is orbiting it, pulling the star off-center in the same way Jupiter pulls our Sun. In a very real sense, Jupiter's mass is large enough that the Sun and Jupiter are better described as a binary system of a star and a very large planet, rather than simply as a planet orbiting a star. The Sun is the dominant partner, incomparably more massive, but Jupiter is not negligible. Jupiter makes the Sun dance in a tiny way, and that dance is detectable. This mutual influence, the Sun's enormous gravity shaping Jupiter's orbit, while Jupiter's comparatively modest gravity influences the Sun's position, is the fundamental physics of the solar system. Everything else, the orbits of the other planets, the positions of the asteroids, the trajectories of comets, all of it takes place in the gravitational field defined by this dominant two-body interaction. When scientists model the solar system's long-term dynamics, they have to account for Jupiter. Not as a minor perturbation, but as a primary gravitational player. The stability of Earth's orbit over geological timescales, the consistency of Earth's orbital parameters over the hundreds of millions of years during which life has been evolving, is connected to Jupiter. Jupiter's presence tends to dampen certain orbital resonances that might otherwise cause the inner planet's orbits to become chaotic over long timescales. The solar system's long-term stability, not perfect stability. There are chaotic elements, but the relative stability that has allowed Earth to maintain a broadly consistent orbit for billions of years is partly a consequence of Jupiter's gravitational influence keeping certain orbital resonances under control. This is, again, not protection in any intentional sense. Jupiter does not choose to stabilize Earth's orbit. Its gravity simply does what gravity does, and one of the consequences is that Earth's orbit has remained within the bounds compatible with complex life for the time needed for that life to evolve to the point of asking questions about Jupiter. There is a circularity here that is difficult to avoid and worth sitting with. We exist partly because of Jupiter. We can study Jupiter because we exist. The questions we ask about Jupiter, the spacecraft we send to explore it, the instruments we design to measure it, are all made possible by a chain of causation that includes Jupiter itself. The king of the solar system is, among many other things, an indirect contributor to the civilization that studies it. Let us now turn to something more immediate and more visceral. Let us think about what it would actually mean to try to explore Jupiter more directly than we have. Not to descend into it, we have covered that, but to establish a long-term presence in the Jupiter system, to build something there, as we have built things on Earth orbit, and as we plan to build things on the Moon and eventually Mars. The challenges are so fundamental that it is worth going through them in some detail, because they illuminate how extreme Jupiter's environment is compared to anything we experience elsewhere. First, the radiation. We have discussed this, but it bears repeating in the context of long-term habitation. Any structure in the Jupiter system would need to protect its inhabitants from radiation levels that are, in most of the Jovian system, immediately lethal to unprotected humans. The shielding required to protect a crew for months or years in Jupiter orbit would need to be dramatically more substantial than anything used in current spacecraft design. The mass of that shielding would be enormous, which creates challenges for getting it to Jupiter in the first place. Some locations in the Jupiter system are better than others. The radiation is least intense in certain high-latitude orbits and in the regions far from the planet. But even the relatively favorable locations are dramatically more irradiated than Earth orbit or the surface of Mars. There is no location in the Jupiter system that is as radiation benign as the inner solar system. Second, the communication delay. Jupiter's distance from Earth varies significantly depending on where both planets are in their orbits, from roughly 600 million kilometers at closest approach to nearly 1 billion kilometers at greatest separation. At those distances, the speed of light delay for communication ranges from about 33 minutes to about 52 minutes one way. A conversation with Earth would involve delays of over an hour for a round trip. Any emergency response from Earth would be impossible in any meaningful sense. A crew in the Jupiter system would be entirely on their own in real time, relying on pre-planned procedures and their own judgment for any immediate situation. Third, the energy requirements. Far from the Sun, at Jupiter's distance, solar energy is much weaker than in the inner solar system. Jupiter receives roughly 27 times less sunlight per unit area than Earth does. Solar panels that would generate substantial power near Earth would produce much less at Jupiter's distance. Any long-term human presence in the Jupiter system would likely need to rely on nuclear power, either fission reactors or, in future scenarios, fusion reactors. This is not an insurmountable challenge. Nuclear power is already used on uncrewed deep space missions, but it adds complexity and mass. Fourth, the gravity well. Getting anything from Earth's surface to Jupiter orbit requires an enormous amount of energy. Getting anything from Jupiter orbit back to Earth requires a similar expenditure. The logistics of supplying a human presence in the Jupiter system would dwarf anything we have attempted in the history of spaceflight. Every kilogram of food, water, spare parts, and equipment would need to be launched from Earth and sent on a multi-year journey to Jupiter. All of these challenges together mean that a human presence in the Jupiter system is not impossible, but it is extraordinarily difficult. It would require technologies and capabilities that do not yet exist and would take decades to develop even under an ambitious program. It would require a level of commitment and investment that no space agency or private company has yet seriously proposed. And yet, the scientific case for closer Jupiter system exploration is compelling. The possibility of life in Europa's ocean alone is one of the most extraordinary scientific questions in the history of our species. If life exists under Europa's ice, it would almost certainly have arisen independently from life on Earth, representing a second genesis, a second experiment in life's emergence under completely different conditions. The implications of that discovery for our understanding of how common life is in the universe would be profound beyond easy description. We sent Galileo to orbit Jupiter for 8 years, and Juno is still there now. We have sent probes past the planet, on their way to the outer solar system. We have done extraordinary science from a distance, but there is a level of exploration that only direct access makes possible, and that direct access will eventually come, perhaps not in our lifetimes, but in the lifetimes of people alive today. When it does, when humanity finally establishes a presence in the Jupiter system, close enough to study its moons directly, to drill through Europa's ice and lower instruments into its ocean, to watch Io's volcanoes from a nearby orbit, to study the structure of Jupiter's atmosphere with instruments that descend farther and survive longer than the Galileo probe did, the things we learn will change our understanding of the solar system and of life's possibilities in ways we cannot fully anticipate. Jupiter rewards attention. Every time we look more carefully, we find more. Every mission to the Jupiter system has returned surprises. The Voyager flybys revealed the volcanic activity on Io. The Galileo mission revealed the evidence for Europa's ocean and the complexity of Jupiter's atmosphere and magnetic field. The Juno mission revealed the diffuse core and the complex multipole magnetic field structure and the widespread lightning. The upcoming Europa Clipper mission will reveal new things about Europa's ocean and habitability. This pattern of discovery, this continuous revelation of new complexity, is not accidental. It reflects something true about Jupiter. It is a world of extraordinary richness and complexity, operating at scales and under conditions that are genuinely beyond our everyday experience. And that gap between our everyday experience and Jupiter's reality means that there is always more to learn, always another layer of complexity to uncover, always another surprise waiting. The beauty of Jupiter in images, the thing that draws people to photographs of it, is real. But the beauty goes deeper than the visible surface. It goes all the way down through the cloud layers and the crushing pressure zones and the liquid metallic hydrogen and the diffuse core. And it extends outward through the radiation belts and the magnetic field and the tidal interactions with the moons and the gravitational sculpting of the asteroid belt. The beauty is not just aesthetic. It is the beauty of something that is genuinely and extraordinarily complex, operating in ways that take generations of scientists to understand, and revealing new depths every time we look more carefully. There is a specific kind of wonder that comes from understanding something beautiful. Not just finding it beautiful, which anyone can do, but understanding the mechanisms behind the beauty, the reasons it looks the way it looks, the physics driving the colors and the patterns and the motions. That deeper understanding does not diminish the wonder. It amplifies it. Because what you find when you understand Jupiter is that the mechanisms themselves are as extraordinary as the surface appearance, and that the deeper you go, the more extraordinary things become. A person looking at Jupiter through a telescope and thinking, "It is a pretty striped ball," is having one experience. A person looking at the same image, knowing that those stripes are cloud, systems moving in opposite directions at 500 kilometers per hour, knowing that that small oval has been a continuous storm for 3 centuries, knowing that the whole thing is powered by heat from a planet still cooling from its own formation, is having a completely different and richer experience of the same object. Knowledge does not diminish wonder. In the case of Jupiter, knowledge is the source of the deepest wonder available. The bare visual impression is striking. The full reality is extraordinary, and the full reality is what we have been exploring together here, from the myth of the guardian planet to the reality of the beautiful monster, from the comfortable story we have told ourselves to the more complex and more fascinating truth, from the name on a star chart to the planet as it actually is, churning and radiating and dominating and shaping the solar system with its indifferent and ancient and overwhelming presence. There is one more layer of this story worth exploring before we bring it to a close. A layer that requires us to think not just about what Jupiter is now, but about what it has witnessed. Jupiter has been present in this solar system for its entire history. It formed in the first few million years after the Sun ignited, making it roughly as old as the solar system itself. And in all the time since, it has been watching in a manner of speaking, though of course it watches nothing and knows nothing. But consider what has happened in the Jupiter system, in the solar system, during the time Jupiter has existed. When Jupiter formed, there was no Earth. The inner solar system was a disk of gas and dust and small rocky planetesimals gradually coalescing. The grand architecture of the planets had not yet taken shape. Jupiter itself was still accumulating material, its core growing, its hydrogen envelope expanding. The process of planet formation was in full chaos. Over the first billion years or so of the solar system's history, as the planets settled into their orbits and the initial chaos of formation gave way to something more stable, Jupiter was the largest gravitational influence shaping the process. It stirred the asteroid belt. It flung material toward the inner planets. It helped clean out the regions between the planets that are now mostly empty space. It participated in the gravitational interactions that set the orbits of the other giant planets and gradually stabilized the whole system into a configuration that has persisted, with modifications, to the present day. During the late heavy bombardment, the period roughly 3.5 to 4 billion years ago, when the inner rocky planets were subjected to an intense period of impacts, Jupiter's gravitational influence was a driving factor. The current best models of this period involve the destabilization of the outer planet's orbits, driven partly by gravitational interactions with Jupiter, sending a wave of material cascading into the inner solar system. The craters that cover the Moon, that crater-saturated surface visible even to the naked eye on a clear night, are partly a legacy of processes in which Jupiter played a role. During the first billion years of Earth's existence, life was emerging. The first self-replicating molecules, the first cells, the first metabolic processes were developing in Earth's primordial oceans, while Jupiter was already a fully formed gas giant ruling the outer solar system. Jupiter was already ancient by planetary standards when life was new on Earth. For the next 3.5 billion years, as life on Earth went through its extraordinary journey from single cells to complex multicellular organisms, from the first animals to the first vertebrates, to the first land plants, to the first dinosaurs, to the first mammals to us, Jupiter was there, unchanged in any fundamental way, continuing to spin, continuing to storm, continuing to squeeze its moons and dominate the gravitational landscape of the outer solar system. Every mass extinction event in Earth's history may have had some connection to Jupiter. When we talk about asteroid impacts, like the one 66 million years ago that ended the non-avian dinosaurs, we are talking about objects whose orbits were shaped by Jupiter. The impactor was not put on its collision course by Jupiter directly, but its journey through the solar system over millions of years was influenced by the gravitational landscape that Jupiter helps define. Jupiter was present for the end of the dinosaurs, and for the Permian-Triassic extinction, and the Triassic-Jurassic extinction, and every other catastrophe in the fossil record, not as a direct cause, but as part of the gravitational environment in which those catastrophes played out. And when our species emerged, when anatomically modern humans appeared roughly 300,000 years ago, Jupiter was already 4.5 billion years old. Our entire species history, our evolution, our migrations out of Africa, our development of language and tool use and art and agriculture and science and technology, all of it happened in the last fraction of a % of Jupiter's existence. When the first human beings looked up at the night sky, Jupiter was there. That bright, steady, wandering light that moved slowly against the stars over weeks and months. They did not know what it was. They gave it names and meanings. They wove it into their mythology and their religion and their understanding of the heavens. For all of recorded history, for every civilization that has ever existed on Earth, Jupiter has been one of the dominant lights in the night sky. And for all of that history, until very recently, we were completely wrong about what it was. We thought it was a god, or a divine sign, or a wandering fire in the heavens, or a perfect sphere of crystalline material. We thought it moved because it was carried by a celestial mechanism of epicycles, or because it orbited the Earth. We thought it was something other than a planet for centuries after we first pointed telescopes at it and resolved it into a disk with moons. The history of our understanding of Jupiter is a microcosm of the history of science itself, beginning with myth and moving slowly, through observation and mathematics and spacecraft, towards something closer to the truth. Each step revealing that Jupiter is larger and stranger and more complex than the previous understanding had suggested. And here we are now, 400 years after Galileo first saw Jupiter's moons, with spacecraft in orbit around the planet, with maps of its magnetic field and measurements of its interior structure, with knowledge of subsurface oceans on its moons and tidal heating and radiation belt dynamics. We know so much more than Galileo did. and we still do not know everything. We still do not know precisely what Jupiter's core looks like, and whether that diffuse core structure truly reflects an ancient giant impact. We still do not know whether Europa harbors life. We still do not know the exact chemistry responsible for the colors of Jupiter's cloud bands. We still do not know the detailed structure of Jupiter's deep winds and how they connect to the interior heat flux. The mysteries that remain are not trivial mysteries. They are central questions about how this planet works and what it means for the broader questions of planetary science and astrobiology. Jupiter will keep revealing things. It always has. It always will. The king of our solar system is not done with us yet. The story of Jupiter and humanity is, in this moment, just getting interesting. The generations before us laid the foundation. Our generation will send missions that begin to answer the deepest questions about Jupiter's moons. Future generations will go further still. And through all of it, Jupiter will continue doing exactly what it has always done, spinning every 10 hours, churning its atmosphere with winds that never stop, radiating heat from its own slow contraction, squeezing its moons, dominating the outer solar system, being exactly what it is, as it has been for 4.5 billion years. We are the new ones here. Jupiter was here first. Jupiter will be here long after we are gone. It does not need our attention. It does not benefit from our study. It has no use for our wonder or our fear. It simply exists. But we are the part of the universe that can look at Jupiter and understand something about what it is. We are the part of the universe that can feel awe. In a cosmos that is mostly cold gas and ancient light and the long silence between stars, the fact that something as brief and fragile as a human being can look at something as old and enormous and violent as Jupiter and think and feel and understand is one of the universe's more remarkable arrangements. Jupiter is the scariest planet. It is not peaceful. It has never been peaceful. It is a world of permanent catastrophe and ancient violence and indifferent power. It is also one of the most beautiful things our solar system has ever produced. Both of those things are true at the same time. And being able to hold both of them at once, the terror and the beauty, the violence and the wonder, the overwhelming scale and the fragile observer trying to comprehend it, that is what it means to look up. If you made it here, you already know what this feels like, that quiet, that drift. But every night it ends. The video stops. The silence wakes you. And you're reaching for your phone at 3 a.m., choosing something new when all you wanted was to stay asleep. Beyond the Stars was made for that moment. 5 deep sleep experiences, hours long. No ads, no endings. Just the night. All the way through. Yours tonight for a one-time purchase. Begin now at mycosmicdrift.com.